Hello everyone, I am Rajeshri, Assistant Professor, Department of Electrical and Electronics Engineering, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be discussing single phase full wave AC voltage controller with resistive load. And previously we have seen for half wave control rectifier. And now we'll be seeing full wave AC voltage controller. So here, if you see this here in this particular circuit, full wave controller circuit, we have two SCRs. One is T1 and other is T2, which are connected in anti-parallel. These are anti-parallel switches, which is connected across supply as well as load. So during the positive half cycle, we are providing the triggering pulse for the thyristor 1. Gate triggering pulse for the thyristor 1 right from this instant called alpha. And again, during the negative half cycle, if you see, we are providing the triggering pulse for the thyristor 2. This is for the thyristor 2. This is the gate triggering pulse which we are actually providing right from this instant called pi plus alpha. So here, the moment the positive half cycle has been appeared, you know very well the polarities will be positive, negative, and here anode of the thyristor is more positive with respect to cathode of thyristor 1. So that is the reason thyristor 1 will be acting as on switch. It will be acting as on switch, whereas thyristor 2 will be acting as off switch or open circuit. So, during the positive half cycle, as soon as triggering pulse is provided, thyristor 1 starts conducting current through the load. So, that is how T1 is conducting current through the load, and this is the conducting path for the thyristor 1 during the positive half cycle. And right from this instant called alpha, here we have provided the triggering pulse for the thyristor 1. So, T1 is conducting right from alpha till pi, and this is thyristor 1. And this is the output voltage which I am actually indicating. See here, where output voltage is equal to I into R, that is the general formula. Here I naught into the value of the resistance of the load, I naught R. That is how we are actually getting the output voltage. So here, right from alpha to pi, we are getting the output voltage due to thyristor 1, and the moment it reaches pi, what happens? Negative half cycle has been appeared. So that is the reason here thyristor 1 will be turned off. Here thyristor 1 will be turned off because of the polarities during the negative half cycle. Now during the negative half cycle, polarities will be negative, positive, due to which anode of the thyristor 1 is negative with respect to cathode. So T1 is turned off, and since cathode of the thyristor 2 is more negative with respect to anode, now T2 will be acting as an on switch. And since the moment at which we are providing the triggering pulse, T2 starts conducting current through the load. So this is how thyristor 2 starts conducting current through the load, and this is the conducting path during the negative half cycle. So the moment it reaches pi, T1 is turned off, and again T2 is forward bias. And at this instant called pi plus alpha, here we are providing the triggering pulse for the thyristor 2. So that is how thyristor 2 started conducting from pi plus alpha, and it is conducting till 2 pi. And the moment it reaches 2 pi, what happens? Positive half cycle has been appeared, and because of which now T2 will be turned off. And again positive half cycle will be appeared. So it remains off until and unless we provide a triggering pulse, T1 doesn't conduct. The cycle repeats. And if you see here, output current is just similar to that of the output voltage. And if you see here, output current or supply current is one and the same. Why is it so? The same path, because it is flowing in the same path. Supply current as well as output current is flowing to the same path. So that is the reason here supply current is equal to output current, and both will be indicated in the same waveform. And if you see, output current is just similar to that of the output voltage, only magnitude will be a difference. As I told you, I naught is equal to V naught by R. So since because of the presence of the resistance, I naught will be less when compared to that of the output voltage. Only magnitude will be less, or otherwise waveform will be one and the same. So the moment when we provide the triggering pulse, thyristor is conducting current through the load till pi. The moment it reaches pi, T1 is off, and again T2 started conduction from pi plus alpha to 2 pi. And this is our output current waveform or supply current waveform. And now coming to this, if you see the advantages. Previously we have seen half wave controller where positive half cycle is not similar to that of the negative half cycle. So their output waveform was not symmetric. Whereas here output voltage as well as output current as well as supply current, all the three are symmetric. So that is the reason here no problem of saturation of the transformer core or the load. So this is an advantage because positive voltage is just similar to that of the negative voltage where the waveform is symmetric. All the three waveforms are symmetric. So DC component is absent, and that is how loads are not saturated or transformer is also not saturated. And if you see, let us check out the waveform of the thyristor. I mean thyristor voltage individually. Voltage across the thyristor 1, VT1, and this voltage will be only appeared when the thyristor is off. It is because when the thyristor is off, whatever the supply voltage which we are actually feeding will be appeared across the load. That is how we will be getting the waveform across the device during its off state, and during on state the voltage across the device will be almost equal to the on state voltage drop, which is almost negligible. So that is the reason here we consider that as 0. And if you see right from 0 to alpha, here output voltage is present, and the moment it reaches alpha, since thyristor 1 has came into the conduction state, here we are getting the output voltage across the thyristor, voltage across the thyristor as 0, and it is remain 0 as long as thyristor is conducting because the voltage drop across the thyristor is almost negligible. So that is the reason here we are considering it as 0. And later voltage across the thyristor is present from pi to pi plus alpha, and again it is remain 0 when thyristor 2 is conducting. And when thyristor 2 is off, again the voltage across the thyristor will be just similar to that of the input voltage waveform. And here again when thyristor 1 is on, here voltage across the thyristor will remain 0, and when it is off at this instant, again the voltage across the device will be appeared, and this waveform will be just following to that similar to that of the input voltage waveform. So that is the thing. Coming to the derivation part, let us derive V0 RMS expression for single phase full wave controller. And this single phase full wave controller, full wave AC voltage controller is also called as bidirectional control. And if you see in half wave control, only positive half cycle of the output voltage is controlled. Whereas here, both positive half cycle as well as negative half cycle of the output voltage is controlled. So that is the reason this is bidirectional control, since we are making use of two switches which are fully controlled switches. Coming to the V0 RMS expression, here V0 RMS is equal to the general formula 1 by T 0 to T V0 square of omega T d omega T. And here the time period is 2 pi, 1 by 2 pi, and it is actually conducting from, let us check out, it is conducting from alpha to pi, that is one interval, first interval, and the second interval from pi plus alpha to 2 pi. So here we are getting alpha to pi, and this is Vm square sine square omega T d omega T plus, and it is again conducting from pi plus alpha to 2 pi, pi plus alpha to 2 pi. which is again Vm square sine square omega t d omega t whole to the power of 1 by 2. And here Vm square, bringing it out, Vm square by 2 pi, and in order to integrate this, 1 minus cos 2 omega t by 2 within the limits alpha to pi plus this is again 1 minus cos 2 omega t by 2 from pi plus alpha to 2 pi. This is whole to the power of 1 by 2. And we get Vm square by 2 pi. And I am taking this denominator out so that it will be convenient for me to integrate. This will become 4 pi. And now integration of 1 is omega t within the limits alpha to pi minus integration of cos 2 omega t is sine 2 omega t by 2 within the limits alpha to pi plus again omega t from pi plus alpha to 2 pi, and integration of cos 2 omega t is again sine 2 omega t by 2 pi plus alpha to 2 pi. We get Vm square by 4 pi. Further simplifying inside, we get upper limit minus lower limit is pi minus alpha minus sine 2 pi by 2 minus of minus plus sine 2 alpha by 2 plus 2 pi minus alpha minus sine 2 into 2 pi is 4 pi by 2 minus of minus plus sine 2 pi plus alpha by 2 whole to the power of 1 by 2. And here further simplifying inside, we get sine 2 pi value is 0. We can neglect this term. Pi minus pi gets cancelled, and here 4 pi term is also 0. So here sine 2 alpha by 2 plus 2 pi minus 2 alpha, adding these two terms, minus 2 alpha 2 pi, and here I am writing this in terms of sine A plus B formula. So here sine A cos B plus cos A sine B by 2. Further simplifying this expression, we get 2 pi minus 2 alpha plus sine 2 alpha by 2, and here this term is 0. Neglecting this term, cos 2 pi value is 1. So here sine 2 alpha by 2 plus sine 2 alpha by 2, we get 2 sine 2 alpha by 2. And here I am taking 2 common and bringing it out such that here Vm square into 2 by 4 pi minus alpha plus sine 2 alpha by 2. This is whole to the power of 1 by 2. 2 gets cancelled. Applying a 1 by 2, we get V naught RMS is equal to Vm root over pi minus alpha plus sine 2 alpha by 2 by taking this 2 pi inside. This is the final expression for V naught RMS for single phase full wave AC voltage controller. And in the coming up lecture, we'll be seeing single phase full wave controller with common cathode. Thank you.